Hello, everyone. Welcome to the Environmental Research webinar. I am Songkyun Park, faculty member of Epidemiology and EHS. So this seminar series is sponsored by the Michigan Life Stage Environmental Exposures and Disease Center, M-LEEaD. So before I introduce today's speaker, so please note that use the Q&A on the bottom to enter your question, and then after the talk, we will cover your question. Today's speaker, I'm very pleased to introduce today's speaker, Dr. Olivia Halabicky. Olivia is a children's environmental health nurse researcher who studies early life exposures and human development. We had our center scientist talk a few weeks ago. So Olivia is one of this year's M-LEEaD center scientists. Her research focuses on how environmental exposures at sensitive period shape neurodevelopment and health trajectories and influence health disparities, as well as physiological mechanisms that may mediate these effects. She employs methods from a variety of disciplines, including nursing, environmental and social epidemiology, and developmental sciences. Dr. Halabicky conducts her research mostly within the element cohort, a Mexico birth cohort that has been followed for over 30 years. So today she will be speaking on early life lead exposure, mitigating harm after exposure. So please join me welcoming Dr. Halabicky.
Hi, everyone. Thank you, Dr. Park, so much. Let me get my screen sharing here. Make our faces really small. So hi, everybody. I'm really excited to be able to talk with you all today about early life lead exposure, which is a topic near and dear to my heart, but really thinking about how we can start focusing on not only prevention of lead exposure, but what we can do to mitigate risk after exposures have occurred. So I'll talk a lot more about that today, but just to set the scene of what we'll go through today, I want to focus in on first why a nurse clinician cares about environmental health. It's a little bit outside of the nursing realm, but I want to talk a little bit about that, and then really get into this problem of lead exposure and some theory and some gaps that really guide my work and thinking about how we can start mitigating risk after exposure. I'll talk about some of the data that I've worked on with two different cohort studies, one in Jintian, China, and one in Mexico City, and then think about moving forward of how we can use this information to start developing interventions, thinking about risk and protective factors and different mechanisms, and looking ahead. So first things first is, why does a nurse care about environmental health? When I give talks, I like to start off with a little metaphor that child development does not exist in a silo. Kids don't have just one exposure or one experience, they have multiple. And that's the same with research kind of combating public health issues. It's not a siloed work. There's multiple disciplines that all come together who have similar questions that we want to answer. And that is something that has really guided my work and my training and thinking about bringing all of these things together. So I got here by first starting off as a nurse in the neonatal ICU at Hurley Medical Center Children's Hospital in my hometown of Flint, Michigan in December of 2015. So for those of you who remember, that was just in the wake of the Flint water crisis. And during this time, children were exposed to really high levels of lead in our water supply, and the percentage of childhood elevated blood levels actually doubled in the city from 2.5% to 5%. That's compared to outside of the city of Flint, where normally that percentage of elevated blood levels sits at around 0.7%. This was a terrifying time to be a nurse in general, especially a new graduate nurse where I'm trying to figure out what I'm doing. But families were coming to me really, really overwhelmed, and rightfully so, about what was going to be happening in this lead crisis and how that impacted their kids. And what they asked me just about every day is, what's going to happen to my child and how can I prevent something bad from happening? And I didn't know what to tell them, and I still am working on what to tell them, but it became really clear that the question that actually needed answering is, what do we do after lead exposure? So that kind of brings me to giving a little bit of history around lead exposure in the US and some guiding theory and some gaps that we need to fill in order to start mitigating risk. So if you're not as familiar with lead exposure and how we conceptualize it in the US, we kind of rely on the CDC to give us some reference values. That always hasn't been the case. There used to be some different terminology. So this acceptable level of lead exposure has steadily decreased. We used to use terminology around thresholds of acceptability, and now we use reference values. And this little graphic just kind of shows you as time has gone on, that rate has decreased. So in the 1960s, a child having a blood lead level of 60 micrograms per deciliter or less in their blood was considered under a threshold. 60 was that threshold. As more and more research has been conducted and we've learned a lot more, that level has steadily decreased. And it was in 2012 that the CDC actually said, okay, it's not a threshold of safety anymore. We're going to pin this to a reference value, which is actually met up with the 97.5th percentile of children's blood lead levels in the United States. And they now recognize that there is no safe level of lead exposure. So even if you're below that reference value, that is not considered safe. In 2021, the CDC actually lowered our reference value to 3.5 micrograms per deciliter in the blood. So that's all really great. And we've also done a lot of really great things from removing lead from really large scale sources of exposure. So in the 70s, the Clean Air Act was passed, as well as new rules around banning lead in paint, which is really great. In the 90s, we finally saw lead being banned from gasoline. And then early 2000s, there's some work with the EPA on tightening restrictions of lead exposure. All that being said, kids are still really, really exposed to lead exposure. Globally, 1 in 3 children have elevated blood lead levels, and this number is actually tied to that 5 microgram per deciliter number. That equates to around 800 million kids, which is not an insignificant number. So there's obviously still a lot of small sources of exposure that kids are still being exposed to lead, even if we've gotten rid of lead in paint and in gasoline. So some of these common sources of exposure, there's a lot of them. You may have seen relatively recently, there's been a lot of reports of heavy metals, including lead, arsenic, cadmium in baby foods. There's a lot of heavy metals, especially lead, that can be found in a lot of ceramic glazes that are used in pots that people might cook with or eat out of. A lot of spices can contain heavy metals. Battery recycling, we love moving towards electric vehicles, but recycling those batteries actually has a lot of long-term effects as far as lead exposure. Iron smelting and obviously air pollution in general can all lead to common sources of lead exposure currently. And what we know through a lot of literature is that there are these longitudinal relationships with early life lead exposure in child and adult health. And decreasing IQ might be the one that you're most familiar with, but there's a lot of other well-known associations with cardiometabolic health and disease, with kidney function, with alterations to pubertal development, as well as sleep latency, other behavioral factors as well. Really importantly, and I think especially in the US, it's important to recognize is that lead exposure is inequitably distributed across populations. So this was a map that Vox put together kind of just in the wake of the Flint water crisis, and they're trying to illustrate your risk for lead exposure depending on where you live. So this map is put out by census tract levels, and at the 1 level, or that kind of deepy purple blue color, is a low risk for lead exposure, and as you get more into that deep burgundy towards the 10, that's showing an increasing risk for lead exposure. This is calculated from a lot of different variables, but really pulling on variables that we know to be highly correlated with a risk for lead exposure in the US, such as socioeconomic status in that census tract, as well as the age of the housing stock. If you live in a home that was built pre-ban on leaded paint in the 1970s, you're at an increasing risk for lead exposure, just knowing that there's probably lead paint in the home. So some people are more likely to be exposed just based on where they live, right? There's also a tremendous amount of variability in the outcomes that are associated with lead exposure. And I think this is the part that I find the most interesting, is that even with similar levels of exposure, some kids are going to do better than others. So this is a really interesting study that used a national data set done by a colleague of mine, Andrew Marshall. And what he's looking at here on that x-axis is that risk for lead exposure using similar variables that Vox map actually used. So thinking socioeconomic status and the age of the housing stock. And he wanted to know how that was associated with cognitive test scores, and then stratified that analysis by income level, which is meant to be a proxy for socioeconomic status. And what he found is that association between increasing risk for lead exposures and cognitive test scores was negative, but really only for those kids from a low socioeconomic or low income household. And really those kids in the high income or even the mid income household seemed to be protected. which might seem like a kind of a negative thing, but I think that this is super hopeful, because what this could mean is that once there are exposures in the rearview mirror, once they have happened, there could still be a chance for protection, because there's something going on in this exposure health relationship that is protecting some children and putting some others more at risk for adverse outcomes. So to get at this idea, we kind of have to pull back, I think, and think really upstream. And that means thinking about all of these early experiences and exposures that influence development and life course trajectories. And what I'm going to focus on here today is how we can think about 3 different frameworks that really inform my work, and how we can think about these early exposures and experiences as influencing health and developmental disparities. So the first one of these is pulled from more of my nursing background, but thinking about Bronfenbrenner's socioecological model and recognizing that there are multiple early experiences and exposures that can set our life course and our health trajectory. And these exposures are simultaneous, they can be repeated, and they might jointly influence the same health outcomes, and they could interact to influence those health outcomes. And they are occurring throughout our lifetime, not just in early childhood, and continually impacting our development. What's really important is that as we experience these exposures and other experiences, we're continually responding and physiologically adapting to our individual context. So those adaptations could be like good, adaptive, they could be maladaptive, they could be a combination of both. Really, our body is trying to respond to what we're experiencing now and trying to get us prepped for what might happen later, even if that doesn't come to fruition. So it is incredibly individualized on that context, on your individual experiences, on your biology, as well as how frequently you might be responding to external stressors. Which brings me to this second framework, which really comes from more of a child development perspective, but thinking about a double hit or a 2-hit model of early life stress. This idea really postulates that repeated exposures to stressors can result in some physiological changes to our stress response systems and some changes to our neurochemicals that influence our development and our health. So, for example, here, if you may have been exposed to a particular toxicant while you were in utero, and then also experienced some psychosocial stressors while you were a child, that's going to increase your risk for stress response system dysfunction. So thinking HPA axis, which is our hypothalamic pituitary adrenal axis, behavioral impairments, and neurochemical changes. So as that moves forward, as we experience these things, to get more into this biology piece, we know that multiple stress hits can result in adaptations via these biological changes that then impact later health. So these physiological changes can take a lot of different forms. So there's cellular, think like oxidative stress, alterations to our cardiovascular, metabolic, immune, neuroendocrine systems, and even some epigenetic changes. And all of this is really conceptualized as a biological embedding of experiences and exposures. And we know that as these changes happen, they can affect our later life health and disease. So if we put all these kind of frameworks together, we can start to understand how even with similar levels of one exposure, like lead, you take 2 children who have very similar levels of lead exposure, there are these other exposures that are simultaneous that can help shape a different developmental trajectory for these 2 kids, which really influences health disparities and health outcomes long term, but also highlights this need for individualized interventions for kids who have all of these different exposures and experiences. And so, setting this groundwork of within lead exposure research, there's a lot of gaps that if we don't fill them, we're not going to be able to develop these individualized interventions to actually mitigate developmental harm after exposure. So this has kind of been my mission in my very short academic research career, but what I hope to do as I keep moving forward. And today what I want to focus on is these 2 areas to talk about how they can be utilized to develop some meaningful interventions. So I want to focus on thinking about double hits of exposures, but then also thinking about biological embedding of how lead exposure could become biologically embedded to influence our later health. So the first example that I want to talk about is work that I did a number of years ago with a cohort in Jintan, China, and really focus on this double hit idea. So looking at the influence of lead exposure as well as parental education and how that could influence specifically adolescent physiology. I'm really interested in adolescence because that's kind of a gap in lead exposure research writ large. We know a lot about how early life lead exposure impacts child health. We know a lot about adult health. Adolescence is kind of like this middle period that we don't really think about as much. And that's really, really important to think about because adolescence is this critical period of biological development, in particular of the autonomic nervous system, which is something I'm really interested in. For those of you who don't sit in and around biology as much, autonomic nervous system is home to our fight or flight response. So the way I describe that is if you're walking across the street and a car is coming up to that stop sign and you do not know if they are going to stop or not, you want your body to do a lot of things to make sure that you can get out of the way. You want your eyes to dilate, you want your respirations and your heart rate to accelerate, you want a lot of different hormones like epinephrine, norepinephrine to be released. These are all really adaptive responses to an acute stressor, right? So knowing that there is this gap in understanding links between early life lead exposure and adolescent health, this is kind of an area I wanted to tap into. And so I wanted to know, how does early life lead exposure impact adolescent health, in particular autonomic functioning? And I was going to do that by looking at a heart rate variability measure, which I will talk a little bit about. So just a word on this cohort that I worked with. This is a cohort out of Jintan, China, and it recruited from 3 different preschools in the area. So kids who are between 3 to 5 years of age, and it actually ended up recruiting about a quarter of all the kids who lived in Jintan. And so there's a initial recruitment in 2004 to 2005, and then a follow-up period starting in 2011 when these kids were in this early adolescent phase, just around 12 years old. And so what I was able to do with this cohort, with the really rich data that had already been collected, was look at blood lead levels in early life between 3 to 5 years of age, and again in this early adolescent period, and see how these were associated with a heart rate variability outcome, which is a measure of autonomic functioning. This was collected through an ECG or electrocardiogram during a public speaking stress task. So what we wanted to do was elicit some stress in these adolescents. And so this task, essentially what they were told is, so they sat down and said, okay, you have 5 minutes to plan a speech, and then you're going to have to give a 5-minute speech to this panel who's going to judge you on it. So it's meant to make you feel a little bit scared. So in doing that, we can collect heart rate variability as they are preparing for the speech as well as delivering that speech. And just a word on heart rate variability measurement. The reason that we're looking at this is because it can give us a window into our ability to adapt to an acute situation. If you are feeling stressed, if that car's coming up to that stop sign, if you're asked to give this speech, we want to see that your body can adapt to that stressor. And that would be high variability. We want a high amount of variability in your heart rate. That shows adaptability. So during this public speaking stress test, there's a lot of different ways that you can take that ECG data. What I did in this particular part I'm showing is looked at the frequency of the high and low power bands within the ECG. Not going to get into the details of that, but what I want you to know is that when you look at a ratio of those frequency bands, this can give us an indication of the balance of the autonomic nervous system. And when we look at that ratio, an increasing low to high frequency ratio actually corresponds with a decreasing heart rate variability. So things might look like a little inverse than how I'm talking about it, but I'll try and ground us when we look at it here. So when we get into the results, what I found with this cohort is that childhood lead exposure was associated with a decreasing heart rate variability in adolescents. So for every 1 microgram per deciliter increase in early life lead exposure, that low frequency, high frequency ratio actually increased, which corresponds to a decreasing heart rate variability, which is maladaptive. That's not showing adaptability to an acute stressor, right? So lead exposure was having a negative impact on autonomic functioning. But I wanted to get at this double hit idea. So I wanted to know if socioeconomic status would modify this relationship. And so what I used was parental years of education, both maternal and paternal years of education. And I hypothesized that low years of education would be this additional stressor, this double hit on top of lead exposure, and might interact to influence this heart rate variability outcome. And so what I found is that parental education did significantly modify that relationship between lead and heart rate variability, but very much in the opposite direction than I had hypothesized. So what I found is that maternal years of education was a significant modifier. And so if we look at this plot here, the gray triangles are low maternal education and the black circle is high maternal education. And I found that as blood lead increased, children whose mothers had high education had a decreasing heart rate variability, which is that maladaptive response that's not showing adaptability to an acute stressor. So it almost appeared, if we were interpreting this, that low maternal education was protective and high maternal education was an additional risk factor, which don't you hate it when that happens, when things don't match the way you want them to? Paternal years of education did not have that same significant modification effect. So it did not appear to have a significant difference. If your father had higher or lower years of education, that same relationship stood. As blood lead levels increased, so did that low frequency, high frequency ratio, which corresponds to a decreasing heart rate variability. And so why did this happen? Why is it that greater maternal education was associated or, causing this significant modification effect? I think this all comes back down to how we conceptualize our stressors, especially in epidemiologic research. And really, there's this big cultural and contextual significance of what's considered a stressor in some places is not a universal stressor. So I was conceptualizing low education as a stressor. That might not be the case in this population. In fact, there's a lot of other things that could be going on. And really, parental education is not a great proxy for social stress. There's lots of other things to consider. It could be that maternal education might be related to household dysfunction. There could be a flipping of gender roles here. It also is true that this is an academic stressor. If you live in a home where maybe your parents have really high education and high expectations for you of what you're going to achieve, and then I tell you to give this speech, that's a really big academic stressor. Perhaps there is something at play here. But I think what's really important to take away from this, especially thinking towards how we mitigate risk, and this clinical significance, is that stressors and by extension protective factors are very unique to individuals, taking it from that population level down to an individual. And if we start thinking about mitigating risk through protective factors, we have to make sure that this is actually something that's perceived as protective to the people that we're working with and for, and not making assumptions about what those things might be. And so moving forward and thinking more about how these things could influence biology, I want to talk a little bit about biological embedding and some work that I have done much more recently with the Element cohort, which is a birth cohort out of Mexico City. I'll talk a bit about, and really understanding associations between lead exposure and measures of biological stress. And I have become, in the past few years, really interested in a collective measure of physiological stress called allostatic load. Allostatic load is this measure, or meant to be this measure, of cumulative body burden of stress. It was originally conceptualized by Seaman et al. Back in early 2001. And there's a lot of variability in how this is measured, but I'm just going to give us the basics. In theory, allostatic load indexes include biomarkers from multiple different body systems, traditionally from these four main systems, so cardiovascular, metabolic, immune, and neuroendocrine. Take a bunch of biomarkers in these systems, create cut points to sum together an index. As that number gets bigger, that signifies an increasing allostatic load. Really importantly, allostatic load takes a long time to develop. And if we think about this just conceptually, this graph, I think, does a really great job of doing that. On our x-axis is stressful stimuli, like hits happening over time. And then on the y-axis is the level of stress mediators that are being released in the body. So think cortisol. As you experience a stressful stimuli, your body's naturally going to release cortisol. Over time is going to bring you back down to homeostasis. So this is your homeostatic recovery. Over time, if you experience a lot of stressful stimuli, if they are chronic and repeated, eventually your body is not able to bring you back down to that original homeostatic set point, and you're going to set a new point. And this gap between the new point and this old point of homeostasis is really this conceptualization of allostatic load. So you can see it takes a while to get there. There's a lot of time until you're going to actually see that development of allostatic load. And so to get there, as I keep saying, it takes a long time. There's a lot of biological changes that have to occur before we get to allostatic load, and before allostatic load can influence adverse health outcomes. So this is a graphic that I've put together to try and explain this as best I can, thinking upstream of allostatic load. We hypothesize, like a lot of people looking at allostatic load have hypothesized that there are these primary effects, primary mediators, primary outcomes, and secondary outcomes. All of these are biological changes that then give way to all of these tertiary health outcomes that we are familiar with, like decline and impaired neurodevelopment, cardiovascular disease, diabetes, liver disease, things like that. If we take this pink circle and kind of stretch it out a little bit more to think of these things that are upstream to allostatic load, we have these primary effects, which are really mitochondrial damage. So think increasing reactive oxygen species or oxidative stress. This gives way to primary mediators. So these are like the mediators of our stress response system. So think cortisol, immune function, things of like the HPA axis, neuroendocrine responses. These can give way to some cellular dysfunction, so epigenetic changes, telomere shortening, which then gives way to some secondary outcomes, which is some organ system changes in the functionality of how our organs are actually going to work. And so the reason that I'm so interested in this is because rodent models have done a really great job of demonstrating associations between lead exposure and neuroendocrine and epigenetic alterations, specifically looking at how prenatal and postnatal lead exposure can influence HPA axis dysregulation and glucocorticoid functioning, as well as epigenetic changes such as accelerated biological aging. And then further mapping how these changes can associate with later cardiometabolic, neuroendocrine, reproductive health in these rodent models. And this is really interesting because this maps really nicely onto the allostatic load model. So the HPA axis dysregulation and epigenetic changes, these are primary mediators and primary outcomes of the allostatic load model, of all those upstream biological changes before we get to allostatic load. And this maps onto these tertiary outcomes of allostatic load. And so I think that this is a really promising future area, and that allostatic load could be a mediator between exposures and health outcomes. It could be that lead exposure impacts how our stress response systems function, which results in cumulative overload or this allostatic load, which then influences later health and disease. And we could use allostatic load and its components because it could suggest early risk. We could get a better reading on how our body is responding to stressors. And then it also could be targeted for intervention. And so giving all that background, I want to tie this into some of the work that I've done with the ELEMENT cohort study. So the ELEMENT cohort is a Mexico City birth cohort, started at Harvard and eventually moved its way to the University of Michigan, and is a really unique partnership with the National Institute of Public Health in Mexico City. And so I'll talk a little bit more about the data set, but we have a lot of different outposts now with different researchers across the country who all work with this cohort, which is a really fabulous interdisciplinary group. So the cohort altogether has had a lot of really tremendous data collected. It began data collection in 1994 with 3 separate cohorts that were eventually merged together to all create the ELEMENT cohort. And this is comprised of maternal-child dyads, so moms who were enrolled either during pregnancy or just after birth, as well as their children, after they were born. And it's 30 years in the making and ongoing. So there has been multiple different follow-up periods throughout childhood and adolescence, and now a future adult follow-up period, as well as different follow-ups with the mothers as well, but focusing on the kids for this particular part. And what I'm interested in is these original maternal-child dyads, so thinking of prenatal and early life lead exposure and other exposures, and how that is associated with adolescent outcomes. Again, knowing that adolescence is a period not as often associated or studied in looking at early life lead exposure. And so what I wanted to ask is how early life lead exposure could influence this cumulative burden of biological stress. So thinking allostatic load in particular. And within this ELEMENT cohort, we have multiple different measures of lead exposure. So a lot of measures in this prenatal period. We have maternal blood lead levels at the first, second, and third trimester, as well as bone lead levels of the moms at 1 month postpartum. And that's really great and unique of ELEMENT in that to have both blood and bone measurements. For those less familiar with lead, it has about a half-life of 1 month in the blood. So when you get a blood lead draw, that's representing of a really acute exposure timeframe. But bone holds on to lead for a long time. So when we get that measurement, it's actually more indicative of chronic exposure to lead. So it's a really great culmination of different measures of blood and bone lead measures in that prenatal period. Then we also had postnatal measures, so blood lead levels for the kids when they were 12 and 24 months old, which is what I used for this study, as well as in adolescence. And then in this adolescent period is where I calculated this allostatic load index from 14 different biomarkers. So I'll talk about those biomarkers just a little bit, but I don't want to harp on allostatic load too much, but really happy to take questions about this. I created this index from 14 different biomarkers based off of the original allostatic load model by Seaman. So essentially, all of these biomarkers, which I won't read off, but came from those 4 traditional groupings of physiological functions, so cardiovascular, metabolic, immune, and neuroendocrine. And then I used the original sample methodology, essentially by taking those sample biomarkers, putting them into quartiles, and then coding them for low and high risk, and then summing together to get that index score. And so what we found in the cohort is that there was this association between, in particular, maternal bone lead and adolescent allostatic load for both males and females, thinking tibia and patella bone lead, showing this increasing allostatic load. And this was one of the first studies to actually look at lead exposure and allostatic load, and the first of them in children. What I will say as a caveat is these were super modest effect sizes. It was not hit them out of the park with significance and huge effect sizes, which is okay. And what I wanted to do is kind of look a little bit upstream, like what I've been talking about with allostatic load, and see, okay, how does lead exposure associate with all of these biomarkers that I used to put this allostatic load variable together? And so what I found is that there was a lot of correlations between lead variables and individual biomarkers. In particular, lead exposure was significantly correlated with neuroendocrine biomarkers, which are those primary mediators of allostatic load, that first step on that pink circle process. So if we look at this correlation matrix, those bottom two rows shows all of our lead exposure variables used in this study, and DHEAS and cortisol, which are our primary mediators, are neuroendocrine biomarkers. And also to mention that CRP, which is kind of in the middle there, which is C-reactive protein, which is a measure of inflammatory response, which is a primary outcome of the allostatic load model. So there is something going on here upstream from allostatic load. And so altogether, prenatal lead exposure in this cohort appeared to be really associated with allostatic load development with these modest effect sizes. So why might that be? What I keep saying is that allostatic load takes a really long time to develop. It could be too early to see these effects. It might be that we have to wait a little bit longer. And it could be that these primary mediators and outcomes of the allostatic load model are actually impacted first and indicative of later allostatic load. And so that's what I started working on. I pulled it back a little bit and looked at a primary outcome of allostatic load, which is here what I use is epigenetic or biological aging. And if you've not worked with one of these variables before or thought about epigenetic age before, it's really showing a deviation off of chronological age. So if our chronological age is linear, right, as time goes on, we get older, our biological age could either be accelerated or decelerated from our chronological age. And we can calculate that through DNA methylation. And there's a lot of different epigenetic clocks that I won't get into too much, but these things have been developed over a couple of decades now to be able to take that DNA methylation data and calculate an epigenetic clock from that. And so what I asked is if lead exposure influenced biological age, and does that timing of exposure matter, prenatal versus postnatal exposure? Again, using the element cohort, so all of these same lead exposure datas, but then these 10 biological age clocks that I won't get into too many of them, but there's a lot of different clocks that we have access to in element, which is wonderful. And what I found was a lot of interesting results that were mixed and hard to interpret. So altogether, it seemed that prenatal lead exposure was significantly associated with these epigenetic clocks, and postnatal lead exposure didn't seem to have that significant effect. In particular, earlier on in gestation and through this chronic lead measurement through tibia bone lead, there was this association with accelerated epigenetic clocks, so a biological epigenetic age that was faster than our chronological age in the cohort. However, as we moved further into gestation and get to that third trimester lead exposure, there was associations with a decelerated biological aging, so a biological age that was slower than the chronological age, which was confusing. If we look at sex stratified models, this is a forest plot of 95% confidence intervals just for one biological clock. But what we found is that for males, this increasing blood lead in the first and second trimesters were associated with accelerated biological aging. So you'll see males there are in the black square and females are in the black circle. So what does this mean? This was mixed results. Lead was associated with both accelerated and decelerated biological aging. And honestly, the jury's out on what that means. Is accelerated or decelerated or neither biological aging adaptive or maladaptive in adolescence? In truth, we have a lot of work to do to understand how epigenetic and biological age alterations actually impact later health. But that is an open question, which is really exciting to be able to dive into. It also appeared that postnatal lead exposure did not significantly alter biological age, but could this change as the adolescents got older? So this was a still early adolescent sample. Might it be different as we get a bit older? We're just pulling this down to some clinical relevancy and thinking about how we can use this to mitigate risk long term. It could be that these biomarkers could be an early warning sign of later health to come and signify a point of like, okay, this is where we can intervene because we can see that there's increasing risk for poor health outcomes later in life. And could this potentially be intervened on to maybe reverse these effects that we're seeing really earlier on at this epigenetic level? And so that brings me to kind of thinking forward, thinking towards interventions, thinking about risk and protective factors and different mechanisms that we can tackle. So I see future directions, for my work and for a lot of work going on, is really falling into these two areas. The first, thinking about how early life exposures, which encapsulates a lot of different things, trauma, social enrichment, as well as experiences such as your perception of what you're being exposed to, how all of this can modify relationships between lead exposure and stress biology or health writ large. And could some of these things be protective? And then secondly, do these measures of stress biology that I'm really interested in adolescence or in other periods, actually mediate associations between early life toxicant exposures like lead and later health? And I think that we have a lot of evidence for this moving forward that we can, again, draw from rodent studies. So a really cool study that came out just a few months ago is showing some really interesting evidence about sources of protection, thinking positive exposure. So in this study, in this rodent model, the rodents had multiple different groups of perinatal as well as postnatal lead exposure, and then looking at those pups and their neurocognitive development and abilities, while also integrating some enrichment. So thinking about like what kind of enrichment activities can be put in the cage that they're staying in, as well as maternal care. And what they showed is that these two protective pieces actually did provide some protection from the effects of lead exposure on neurocognition. And this will be a little bit small to read, but this is looking at male and female associations specifically for that perinatal lead group. And what they found is that looking between this non-enriched and the enriched environment group, as well as the low maternal care and high maternal care groups, that there were significant differences in that neurocognitive functioning, the tests they were looking at in these rodents. So there does appear to be some form of protection. How this translates to humans, I think, is still up for debate and, up for a lot of research in the future. But this signifies that there could be some protection involved here from other exposures going on simultaneously. In human studies, we've done a little bit more thinking about mechanisms and how they influence health and interventions that can prevent disruption. So, I'm thinking in particular about stress response system function, which is a function of allostatic load. We know in humans that having an increased allostatic load can cause this disruption and link to later health and disease. But there's been other studies in humans that have shown that some particular interventions, like a sleep intervention perhaps, can actually reverse those allostatic load pieces, revert it back, and help to reduce risk for later health and disease. So this could be another point of intervention, if we better understand this mechanistic relationship between lead and later health. And altogether, what I think is really exciting is that cohort studies are really great opportunities to be able to ask longitudinal questions about risk mitigation, either through thinking about positive exposure. So I've put a lot of pieces here, ACEs being adverse childhood experiences, heavy metals, BCEs are benevolent or positive childhood experiences, and all these structural factors. But we can ask questions in longitudinal studies about how positive social experiences can provide protection. And we can also ask about biological mechanisms. So here, my example is cortisol regulation and how that may mediate associations between exposures and adult health. All of these different time periods could really inform our understanding for potential community and clinical level interventions. Thinking of bringing this down to the family and communal level, or how you interact with your provider, and thinking about positive experiences or ways that we could intervene in an exposure way, or in rolling back some of these mechanistic changes that put you at risk for later health outcomes. And so looking forward and thinking about mitigating risk, we have some gaps to be filled. We need to be thinking about multiple levels of exposures to both toxicants and non-toxicants. I'm always going to be focusing on lead exposure, but I know there's other things that kids are experiencing that is probably providing risk or protection for later health. Focusing on stress biology mediators or other mediators between these associations of lead exposure and health, and thinking about how early life exposures and biomarkers can influence our health outcomes long term. And then taking both of these pieces and really developing interventions that can target these modifiers and these mediators to help mitigate risk across the life course, even after lead exposure has occurred. And so I've listed out kind of what I think are some really interesting future directions and opportunities. So again, thinking about that full picture of multiple toxicants and social exposures, nutrition, sleep, behavior, our perception of exposure. And what I mean by that is to empower people who have potentially been exposed to know what they can do next, which can actually help them physiologically better cope with what is happening to them. But thinking about all of these as targets for intervention, and then really pulling in this mediation piece of thinking about about what are our mechanistic pathways and how could we potentially intervene within there. And these can be implemented into some new approaches. So thinking about expanding observational studies to include these types of interventions and target these pathways even after exposures have occurred. And then really importantly, translating this down to interventions at the clinical and community setting to really empower communities to not only prevent exposures in the places that they live, but also feel empowered to respond after they may have been exposed. And if we put all of this, on a timeline, we can really integrate a lot of early life interventions to help mitigate risk even after lead exposure has occurred. So I've labeled all of these here of thinking about perceptions and sleep and nutrition and behavior. And there's so many things that we can think about. But there's a lot of things on this pathway that I believe we could really start targeting to help protect children even after lead exposure has occurred for them. So if we do this, if we better understand this contextual and multi-exposure relationship and biological adaptations or that biological embedding, we can start to develop individualized interventions to help mitigate developmental and health harm even after exposures. And I think this is really important because reality is environmental exposures and inequities are going to continue to happen. Until a lot of things changes, we're going to have lead exposure. And it's not just that, it's air pollution and heat and wildfires and PFAS and pesticides, like the list goes on. And these things are going to continue to impact the patients that are coming to the hospital, to who we see as public health professionals and people within our own communities, and likely ourselves as well. So if we start getting at these questions, I think it's really exciting because we can start to answer the question that it was once asked to me of what do we do after an exposure? And we can actually have an answer for that. So thank you, everybody. I think really important to say, especially with this work of it would not be possible without the wonderful families and all the cohorts that I work with. If they didn't keep answering the phone 30 years later, we wouldn't have such rich data and participants to be able to work with. So thank you to everybody, and I'm super happy to take any questions.
Great. Wow, this is amazing data, and yeah, it's an excellent presentation. So we already have several questions, but for those who have any question, please use Q&A. So we will cover your question. And Olivia, so for those who will be watching these videos, I will read the question, and you can also look at the question from the Q&A. The question from Dr. Jerome Riagu: how does the fact that lead is a cumulative poison fit into your narrative on allostatic load?
Yeah, I think that's a really interesting question. Gosh, yeah. So for those less familiar with lead, lead is really interesting in that it can kind of mimic calcium in our body and deposit itself in the bone. So yeah, it can hang around for a long time. I think it fits within this allostatic load idea because if you are chronically exposed and you do have these deposits in your bone that are continually exposing you, and we also know that there's times in life when we naturally leach calcium out of our bone, right? So during pregnancy, during menopause for women is really important. If you have lead there instead of calcium, it's going to leach out as well. I don't think that this is only an early life period. I'm so incredibly biased that I love childhood, and so that's what I like to think about. But I think that it fits because allostatic load could be changed throughout our life course. So as you are continually exposed or chronically exposed to lead, this could just be a continual hit over and over and over again that's potentially causing some of those biological embedding pieces and increasing allostatic load.
All right. So the second question from our doctoral student, Sonyoung Park. I'm curious how much the TBR lead level was correlated with the blood lead level. Is it high or low, or overlap between these?
Quite high. So also think that in this particular cohort, these people were pregnant, which is a time that you naturally would leach lead from your bone if you do have lead that's deposited there. So they were really highly correlated. The reason I like that bone lead measure so much is that it's able to look at this cumulative prenatal exposure versus just a month kind of specific exposure of that maternal blood lead at first, second, and third trimester. That just gives me a window, which is interesting, but I liked that bone measure because it's able to give you that full time span, but very highly correlated between those.
And the next question. So I'm Patience Ajulukchukwa from Nigeria, and applicant to Michigan School of Public Health. As someone who lives in rural African community, I've seen firsthand the challenge of access to clean water. Considering the seminars focus on lead exposure, I'd like to ask what alternative water treatment method can effectively reduce lead contamination?
Yeah, well, that one's near and dear to my heart as a former Flint resident. I think it's really important to think about like systems level versus personal level. So systems level is we need to replace a lot of infrastructure. So the reason that this actually happened in Flint and a lot of other communities is that the pipelines that are leading from the water source to people's homes are really old and they have lead in them. So lead is naturally going to leach out into that water system. Once you get like into the home, what you make individual choices is there's a lot of really good water filters that can happen that you can use to reduce the amount, the parts per billion of lead in your water source. I wish that there was a better answer to this question aside from a lot of system changes need to be made because filters are expensive and they need to be changed a lot. So it's something that I think more policy work needs to be done versus that individual work, which I didn't touch on a whole lot in this talk, but I'm not sure who it was. I'm happy to talk about that more at another time of like how we can start thinking about policy to influence where our water sources are coming from, but also other sources of lead exposure, because it's not just water. And in fact, there's a lot of other big sources besides just water.
Was there any like some pattern across the allosteric load markers? For example, some people with high inflammatory marker level have higher or lower levels of other markers.
Yeah. This is I love this allostatic load variable and I hate this allostatic load variable because it's hard to put together because there's not a very clear-cut guideline as to how to do this. It's really conceptual and then you're trying to quantify this at the end of the day. So a lot of the profiles that I looked at did have high inflammatory markers, really high immune markers, and those neuroendocrine biomarkers, so cortisol and DHEAS. In this adolescent cohort, there weren't a lot that actually had like high cardiometabolic indicators. So like blood pressure wasn't through the roof. Their total cholesterol wasn't super high. These were 14-year-olds. I wouldn't exactly expect them to have developed those types of changes at that time period. So I think that a lot more work needs to be done. And what I'm really excited about in this cohort is we're going to be bringing these kids, they're not kids, they're 30 years old now, back in this upcoming year. And hopefully I'll be able to recalculate allostatic load to see how this has changed from adolescence into young adulthood. So, it'd be around like 10 to 15 years or so. So I think that could be super interesting to see how maybe more of these cardiometabolic indicators might actually be showing some sort of dysfunction or positivity at this point. But yeah, a lot of the profiles were showing more neuroendocrine and inflammatory elevated biomarkers, which then you wouldn't necessarily see a high allostatic load because you're putting all 14 of these biomarkers together. So that is a love-hate relationship with allostatic load in my world. But I think it's really ripe for some really cool interventions and work later on.
All right. So the audience, Jennifer Smith. So incredible talk. Did you stratify element result from allosteric load by SES? And if yes, did you see a larger effect size when stratifying by SES?
You're reading my mind. That's the next thing I'm working on. So I haven't done it yet, but that's exactly what I want to do. And we have another really interesting variable in element. It's called the home score, but it's essentially looking at, it was an in-home observational score that looks at the level of parental enrichment, what kind of like enrichment activities were in the home, what sort of neighborhood enrichment activities there are. And I also want to add that kind of into these models to think about how socioeconomic position, yes, but also these levels of enrichment might actually modify this association between lead and allostatic load. So I haven't yet, but it's on my to-do list.
Another audience, so Ethan Davis, do you think lead level would increase or decrease in multi-generational family homes or single-generation homes, considering more family members to take care of children?
That's interesting. So lead levels, it depends on the source of lead exposure. So I think that one of the really interesting things to think about and be careful about and how we think about risk and protection is what is a common source of lead exposure in a particular population. In the US, we rely really heavily on thinking about risk for lead exposure based on socioeconomic status and the age of the housing stock. That's not true for every community. In fact, the first cohort that I talked about in Jintan, China, the biggest source of lead exposure is from battery recycling plants in the area. It's not from paint in old homes. So I think that this intergenerational transmission probably depends on that source of lead exposure and where you're being exposed to it from. Some people, their greatest source of lead exposure could be that your parent works in an industrial plant and brings lead home on their shoes from what they've been walking in, and then a small child puts that in their mouth. I mean, and that's how you could have that, I mean, intergenerational transmission there, but it really depends on that source of lead exposure. And I always want to be really careful in thinking about where lead exposure is coming from in different communities and trying to like honor that and thinking about risk and protection. So yes, there could be in some places a transmission, but not every place, I wouldn't think.
We have a question from Dr. Gil Oman. Do you perceive any difference in susceptibility between Flint and Mexico City population?
Susceptibility to lead exposure, maybe?
I think so. Yeah.
I'll answer it that way. Yeah. That comes back to the sources of lead exposure. So in Flint, the biggest source was from the water supply from that infrastructure of the pipelines, as well as it's really old housing stock in Flint. So a lot of the homes still have lead paint. In Mexico City, the biggest source of lead exposure is actually more diet related, thinking about the types of ceramic glazed materials that people are cooking in. That's the biggest source of exposure. And that doesn't really follow socioeconomic gradients. That's everybody using it versus, in Flint, that did follow a socioeconomic gradient. So I think that there is a huge difference in susceptibility to lead exposure based on where you live and a lot of cultural practices and maybe what industrial plants are around you. A lot of differences. So yes, different susceptibility for sure between Flint and Mexico City.
Yeah. So this is great, and because we go too fast, I really want to ask you something about you train in nursing, and so that's why you are very unique. You have a very unique experience, and then having some like a different perspective in terms of this more primary care and the environmental health. And can you speak as your final comment? Can you speak about role of a nurse in environmental health?
Yeah, I would love to, because I think that nurses don't talk about it enough. And that's kind of my soapbox that I get on. Nurses are usually the one who are taking kids' blood levels. And they're usually the ones reporting back to families of if you're above the reference value or below it. I don't think that currently, at least, nurses in the US is where I have experience that we are given a whole lot of education as to what that means and what we should tell patients about sources of exposure and how to remove those from your home if your child does have an elevated blood level. And then also, this later piece of what can you do if you have been exposed? What are some things that we can recommend to our patients to be able to mitigate risk long term? I think that there needs to be more environmental health education at the undergraduate level for nurses in recognizing that these exposures exist, because I think that there is a common misconception, especially around lead, that we've taken care of it, that we don't need to worry about that anymore. It's already done. I think that this could be really nicely integrated into undergraduate curriculum, but also in clinical practice, especially at the community and outpatient level. I think that at the acute care level in the hospital, usually you're there for something else, not for lead exposure, unless you have an extremely high level and need chelation therapy. But at the community level, I think that there can be a lot of education on the part of the nurse who sees patients really frequently on, hey, have you checked your windowsills? Do you see if there's lead there? Maybe if you are pregnant, maybe you should go get your blood levels taken. That's not a mandated thing. You don't have to do that. But I think that could be recommended for people who are pregnant to get that checked, just to see, are you being exposed? Because you really don't want to be exposed at this really critical time for fetal development. I think nurses could have a big hand. I could talk about that for a really long time, but I'm excited to try and see and try and get environmental health more into nursing spaces, because we talk with people every day who are exposed, and we can help other public health professionals start thinking about this problem.
Yeah, thank you. So 15 minutes is not enough to learn everything from you, but I really appreciate your excellent presentation and the Q&A.
Thank you.
Thank you, everyone, to stay until the end of this talk. And we will have one more researchers and residents webinar in 2 weeks after the Thanksgiving. So have a wonderful day and a wonderful Thanksgiving break, and then we will see you after the break.